we would like to be able to take limits and derivatives of vector-valued functions. Now, first of all, a vector is just a housing unit of things. You can't actually take a derivative or a limit of a vector, so we need to define the operation to our own purposes. So starting with this vector-valued function, if I said I want the limit as t approaches some value of r of t, what we're going to do is define that to be the vector of limits. So if we define the limit of a vector to actually be the vector of the individual limits, then this makes sense because x, y, and t are just functions. So each of these would produce either functions or individual values. So we still have a vector. We haven't changed that aspect. Now, using this definition of limit, we can now define the derivative of a vector. Now, we know from Calculus 1, the definition of the derivative of any function is the following limit. I'm going to rewrite it by pulling the 1 over delta x out in front. It doesn't change the value, but it allows us to use this form for vectors. So now I want to take the derivative with respect to t of the vector r of t. The formal notation we usually use is dr dt, still in vector form, or r prime of t, again, still in vector form. But using this structure, this will become the limit as delta t approaches 0 of 1 over delta t times the quantity r of t plus delta t minus r of t. And as you see, this has the same structure as the regular derivative we learned in Calculus 1. So now that we know that the limit of a vector is the vector of the limits, we can continue on this. Now, continuing on this, if I take the difference of these two vectors and then I distribute the 1 over delta t, this will actually give us the vector of the limit as delta t approaches 0 of x of t plus delta t minus x of t all over delta t, comma, the limit as delta t approaches 0 of y of t plus delta t minus y of t all over delta t, comma, running out of space here, the limit as delta t approaches 0 of z of t plus delta t minus z of t over delta t. And once again, since x, y, and z are simply functions, each of these looks familiar. Each of these looks exactly like a derivative, meaning my final answer would simply be dx dt, dy dt, dz dt. And we've established then that the derivative of a vector is quite simply the vector of derivatives. Now let's look at a few examples. Now let's consider a simple vector of this form here. This is my position. Then the first derivative would be the vector of derivatives. I do not need to take the limit. I already know how to do the derivatives. So I would get 8t e to the t negative 2 sine of 2t. But I can also talk about the second derivative of a vector. In this case, that would be 8 e to the t negative 4 cosine of 2t. So taking derivatives of vectors is the same as taking derivatives of functions. Let's try another one. All right, let's try another example. This time I'm going to use the other notation for derivative. Now in the first case here, you notice we have a product, so I have to use product rule. So first times derivative of the second plus the second times the derivative of the first. The derivative of inverse tan of t, 1 plus t squared. And finally, the derivative of a constant, 0. Sometimes people forget the 0, but if I lose the 0, I no longer have a three-dimensional vector. So that part's actually critical. So if I want to evaluate a derivative, now if I said I want to evaluate this derivative, let's say at 0, then in this case here, if I evaluate this at 0, notice we would get 0 plus 0, 1, 0. So the proper form is the derivative evaluated at a number in the same way that I would express a position vector evaluated at the number. So now we have derivatives and limits